Good afternoon. We're already in the midst of a discussion because we just picked up the quiz, and John, since you've already had the quiz, I can talk about it right now. So at least I did see that you emailed it to me before I came down to class. So the question is on number 2, the periodic power signal that had a power spectrum. So to get the average power, you just integrate that, and it's integrating 3 delta functions. Do you remember I said that's shifting property, so that's easy to do. That would just be the sum of those values, right?
So it's just 40 watts, right?
Yeah. Right? To get to the autocorrelation function domain, you have to inverse Fourier transform term by term. So you get 10. I'm just reading off of Chris's paper since that's what's on the top here. Get 10. So you get a DC value of 10. And then you get a cosine wave at 20 hertz, which is 40 pi times tau. And then the amplitude is going to be 30 because it gets divided in half. It gets split between the positive and the negative frequency. Right? When you Fourier transform a cosine wave, you get half of the spectrum at the positive frequency and half at the negative.
You didn't have that half scenario to factor that half out, which means double the 15 to 30, because 30 halves is 15.
But it's like 15 impulse.
Yeah, it's 15 in the frequency domain.
And then it gets halved, right?
It gets doubled back in the time domain, because when you start in the tau domain or time domain, it's just play it backwards. And you can always do that, right? You could get your answer and then say, wait a minute, if I transform this forward, I should get what I started with. Just simple.
You still made me second guess myself all over that damn quiz.
And the first problem was an even function, right?
Yeah.
So that part was real. And then, yeah,
I wasn't sure.
you can work it into the cosine with a sinc. It should be, you have a sinc squared and then a sinc for the rectangle. And yeah, they both have the same argument, right? Because the triangle's base is 4 and the rectangle's base is 2. And the discussion I had earlier, the definitions are different, right? The triangle is always half of the base width, and the rectangle is the full width. And that's, I suspect the authors created it that way because when you convolve 2 rectangles of the same width, you'll get a double base width and it'll be a triangle. So I think that's why they created it that way, right? Rectangle convolved with itself will give a triangle, and the width will be double.
Never thought about it that way.
Yeah, well, I do, because I'm trying to understand why did you create the definition that way, and I think that's the reason why they did that. You will not find that a universal definition. This book uses capital pi and capital lambda. Other books use RECT for rect and tri for triangle. So in my Python function, I called it rect and tri just because that's something that I can write down in a computer code as a function name. I can't use the abstraction. Well, if you code in Mathematica, though, if you've ever done that, you can use any Greek letters you want to there for function names. You can be real cute about everything, but that's not...
Yeah, we've learned enough languages.
Yeah, that's not practical, though. Python and C are hands-on languages that we do actually do things with, so... Well, it seems like things looked better than they did last time. So now we'll get into what we're going to do. So as a synopsis, though, here's what I wrote late last night. I think after I don't remember when I wrote it, because I've went to rehearsals Tuesday and Wednesday, and I have another rehearsal tonight. So when I play a lot of music, I tend to have 2 phases. I have my go home, go to play, and then I come home much later, and that's like the day has already switched pages or something, but it hasn't. I mean, it's just, what did I do? But at any rate, I wrote this out. Was this better correlated, or was this reasonably correlated, or was the verbal thing that I said in class the thing that was more memorable? Because I felt like I told you what I was going to do, but then I decided I should write it out just to make doubly sure that you can see it in writing, which,
Honestly, I didn't even look at that. I
Okay.
just remember you saying it. So.
okay, did this writing have any impact, or,
I didn't know it was there.
pardon me?
I didn't know it was there.
Okay, well, remember, I always write on the what's new page,
He
so
really does.
the what's new column.
I'm really bad at reading that.
I do it because I don't
I
have,
didn't even get to those problems in this.
yeah.
I always focus on the first 4.
Okay, well, I'm always writing, I'm always authoring on my web pages, and Dr. Platt and I worked on a thing many years ago that was when we first started teaching with screencasting like this, where he created a website. He hired somebody to do a PHP programming thing, and the thing he created I could never use it. He got to use it on his own web server that he still runs in his office, I think. So his thing was cute in that he would load everybody's password in, and then he had the feature that we created was the what's new page or anything new that gets posted to the site would automatically send email messages to the student. So you would be getting these messages saying, something's new up here, you better go take a look. And I didn't do that. The only thing I added, which was sort of passive automation, is I have this thing across the top here, which is reading a what's called server-side include. So if the document changes, then a new time date stamp is on the file name, and then the server-side include, when you bring the website, ping the web page, it loads in by automation the latest file date. And that's kind of another really low-cost way of saying, I better see if he posted anything. You'd have to know when the last posting was, and you just know that it's been changing. It'll change whenever I make a change to the page. If I push a new document up, though, it will not change. But if I push a new document up, I try to faithfully write in the news page, and then it will save that web page again, and then it will have a new time date on it. That's about as far as I've gone. I don't know what's the CMS system we have right now. Course management system is
Canvas.
Does Canvas send messages?
Oh, yeah.
Yeah. It even does, it actually updated it now so that it'll do phone notifications
Okay.
whenever something's changed.
Yeah, I get it all. I get notifications.
Is that
all the time.
good, or is it annoying?
It's good.
Okay. So I'm cheating you out of that capability right now.
Whatever. Adapt and overcome, man.
What's that?
Said adapt and overcome.
Yeah.
It's not the end of the world, so.
Yeah, I'm glad you can say that, because Colton and I had a question about what is it that he's trying to get used to Python, and I said, I'll go back and use MATLAB, or I'll use the free Octave MATLAB syntax. I'll use whatever the customer wants me to use.
Don't get me wrong, like, I spent more time on this homework troubleshooting that stuff you showed us in Python
Yeah.
last Tuesday than I actually spent doing the homework the last couple days. And that's super frustrating because I want to do the work, not the troubleshooting. So.
Yeah.
But
Well, I troubleshooted too, because I had to finish solutions for my phase lock loops class, and I wanted them to do something with this root locus function, and it turns out it doesn't work as well as I thought it would. There's an error not in the stuff I told you about, but the function that somebody wrote for this control system package for Python, it has a graphics error. So if I call it twice, it then throws up an error message. And so I could show you another technique to get an interactive plot, and that's just simply,
nah, man, I'm just gonna make plots.
yeah, just make plots the way, and if you ever want to get access to a plot, let me just show you what you can always do if you want to. You can just simply go up to here and take that word inline away. If you take that out of there and restart your kernel, the plots will come up in a separate window, kind of like they do in MATLAB.
So there's an option if you click on a plot and you right click on it, you can pop it out into a different tab on your Jupyter notebook.
Okay?
Yeah, no, because that's the only way I couldn't get.
Yeah, well, you can do that too. I mean, there's other things. So it's on here.
Yeah, it's something in there about putting on a new tab.
At any rate, there's a lot of different flexibilities with this.
Yeah, create new view from output. Click on
Yeah, that's, well, okay.
further down, 2 down, up, 3 up, 2 up, there you go.
Okay.
And it puts in a tab, and you can slide it up or you can leave it down there, but it leaves it there, which is really nice. So if you go ahead and change something, then you can just see that update there without having to scroll down through the umpteen million. You didn't.
I just moved it into a side window, but
For me, when I use the spectral line plot, I still get, for every iteration it does, it says invalid side type, no matter what I do with it.
yeah, I don't know. I did mine and it ran fine, but at any rate, there's lots of different ways you can use these tools, and there's even more that I didn't show you that are built into this. I'm just looking for things that I'm interested in making use of, and I'm going to fail
So if you
periodically.
take that inline comment out and it does pop it into a new window just like that,
Yeah.
when you export to Typora, what happens to those images?
I don't think you're going to have them. I don't know. I haven't tried that.
Okay.
So I think you're wanting to know how hard or how easy it is. What you'd have to do is just say, I'm going to restart the kernel by hitting the little circling thing, and then rerun that cell. And then, because I like scalable vector graphics as opposed to PNG bitmaps, I would do that. And then I was doing this little picture here. What was it? Where I created the triangle, so I had this little function that created the periodic triangle, and this was useful in the homework. I used it in my solution at least. So now when I hit this graphic is stored in here, and it will render out to Typora. But suppose I never had that graphic, which I can get by right-clicking and say clear output. So now it's gone. I hit this, and now I'm going to see this little icon, and there's my plot window. So my plot window's down there. I can do these things. I can, at this point though, I can save my plot to a file. I can save it as a PNG, a PDF,
Then you can
an
bring it back to
SVG.
Typora.
Yeah, you could do it that way if you wanted to. But this is kind of old-fashioned because this is the way it was in MATLAB, right? MATLAB always opened up a separate plot window, and then you don't have it embedded inside that document. When you open it up, you just have it hanging up on the outside. So
I know there's two kinds of MATLAB files. There's the normal .in file, and there's the mlive or whatever,
okay,
and it generates a separate column of graphs on the right side.
okay, that's something new. I haven't played. I mean,
It's pretty glitchy. It doesn't work very well.
yeah. Well, MATLAB had a notebook. They had a notebook a long time ago too, and I tried to use it too, and it never worked. But they're feeling the heat these days. In other words, they have to do something, or maybe be knocked out at some point in the future, which it wouldn't be the first time with capitalism, right? That's the way we run in the U.S. Capitalistic systems compete or die, right? That's pretty much what we are. So things like that happen. Legacy is legacy. It's not always what we think it is. I'm just going to get this set back up for where I want to go to. I put all of this up, and this should be helpful with the lab. I know Colton wants to ask me a question related to the lab and justification of power spectral density. What is it good for? Because right now, I haven't told you enough to make you really convinced that the power spectral density has value. Yeah, autocorrelation has value.
I know
And-
density spectrum does. I just don't know how to use it yet.
Yeah, well, the thing is that without introducing random signals, we don't really get the full value out of it, and that doesn't come until COM2, and that requires random variables in particular to carry that through. Because the levels, remember, are probability, random variables, and then random processes is the next level above that in sort of that climbing stack of things. Statistics is kind of off to the side. You spend time on statistics in the 3610 class because that's a manufacturability. It's just got a huge number of applications. Everybody in sciences knows something about statistics, no matter whether or not they've even taken calculus. Have you ever noticed, or maybe you have a family friend or a spouse maybe that went to college and didn't do calculus, but they took like statistics for the sciences or something like that, a non-calculus based. One of my sons, who's the architect, he had calculus in high school, but then he didn't need anything beyond calculus, first year calculus for architecture, but he did need a stats class because he did a minor in business. So he took stats for business majors or something like that. He actually took it here at UCCS one summer when he was home. He went to K-State for his degree, but I think it's a shame, but you know, you can do it without it. You just don't get as much out of it. You don't have the calculus aspect of it. But do you need that? I don't know. This is that time of the year when all the predictions are going on with the statistics and the polling, and a lot of that stuff doesn't really use calculus either. It's just sampling a population and producing some estimates of what you expect. And we definitely know about estimating because we learned that at a young age. Take 5 measurements, and what's the true measurement? The best estimate would be the average of all those measurements, right? And those sorts of things. So I'm gonna talk a little bit more about autocorrelation and what you can do with it in an example that's not in the notes here, but it's out there, and I'm gonna pull it in. So I did talk more about the PN. I would like to say a little bit more about the PN code generator because it is so popular in communications applications as a bit sequence for testing out a digital communications link. And like I said before, it's useful in spread spectrum coding where you're actually doing a correlation. You're not just looking at the spectrum, you're actually doing what I've been trying to represent with sliding one hand past the other. You're looking for that alignment. So, and Chris experienced that in the project for modern DSP. It was GPS tracking, right? And that uses not an autocorrelation, but a cross correlation. Auto is when you take the signal you have and correlate it with itself. Cross correlation would be like in a radar application. I transmit a signal, a piece of that signal bounces off the target, and then I correlate that received signal against the local signal, and that would more formally be called a cross correlation because the signal has gone through space, it's picked up some of the artifacts of the propagation medium and energy reflectance off the target, but then when you cross correlate that, you get a correlation peak, and that peak will take on the delay, the round trip delay from the transmitter to the target. And it'll show other nuances, like if there were multiple reflections, as in multipath, you'll see a strong correlation peak, and then you'll see next to it some weaker peaks, which will be the signal that bounced off of other things further away. So like echoes or reverberations, and that makes sense, right? You surely understand that from sonar. You'd get a blip back, but you can correlate with the local signal against the received collection of waveforms, and then you can get a stronger indication. The correlation operation tends to filter more noise out. You know, when you cross correlate, you'll tend to remove more noise and get a stronger measure of the likeness of what comes back to what you sent, and kind of suppress the noise. So an example of that, simple example that I put in the notes, in the Jupyter Notebook, is cross correlation and signal delay. So this is the same definition we have, except rather than x with x delayed, it's x with y lagged by t plus tau, and then the definition is the same as we've had. And there's a function that I have, it's in scipy.signal, but originally I wrote a version of it in the digital comm module, which is in scikit DSP comm. So I import that, and then I have access to XCore, which stands for cross correlation. I generate a PN code that's 6 stages long, so that's going to be 2 to the 6th minus 1, which is going to be 1, it's going to be 63, right? Is that right? 2 to the, let's see, 2 to the 8th is 256, 2 to the 7th is 128, 2 to the 6th is 64, right? So it's going to be 31 or 63 bits long. So I do that. I do some extra processing in here where I'm upsampling and doing some multi-rate thing, which I'm not going to try to explain right now, but I end up creating a delayed signal. So I add in some delay on one of the signals, 35 samples of delay, and then ultimately I come down here and I get, instead of Rx or Ry, I'm calling it Ryx, and I'm doing this X-core where I'm going to actually autocorrelate or cross-correlate X with Y. My function returns also the time lag index for plotting. So in this particular case, I'm plotting the two waveforms, and I did some zero padding in here. That's some of the extra gyration, so they both start at 0, but the delayed signal has 0 stuffed in at the front. So here we've got the signal and the signal delayed, and then the autocorrelation function shows that there's a -4, and you're saying, but wait a minute, it should be delayed. Well, it has to do with the order that I put it in here, so let me just swap these around. So when I correlate X with Y, it's looking like X is earlier than Y, so it's saying it's negative because it arrived earlier than Y did. But if I do it the more logical way, I'll take Y, which is my return or echo return, correlate it with X, and now the autocorrelate or the cross correlation triangle shape that we've seen before comes back delayed in time, and that'd be the physical scenario if we are trying to measure round trip delay to a target or something. I mean, it's just a matter of this business here, which is earlier, which is later, and I can get the negative sign just by having the orientation backwards. And that makes sense, I think, doesn't it? If I lose track of which came first, X or Y, but I know if I send something out in space, it's not going to arrive sooner than it leaves, so I'm pretty safe in just saying it's the absolute value, actually. It wouldn't come back earlier. But in a multipath situation, we could put in more, and then there'd be more peaks. There might be a precursor because there might be something near which doesn't reflect strongly, and then there might be some more peaks, smaller peaks afterwards, which would be the multipath. And in spread spectrum for third generation cellular, they have the ability to do what's called a rake receiver, which actually takes and correlates with multiple correlators and tries to reassemble the signal so it can get a stronger signal by combining the main peak there and then the weaker peak, saying that they all are, the signal arrives at us due to through multipath, and we're trying to harvest as much out of the channel as possible by combining signals. This is not a radar application like this example is, but it would be transmitting from A to B. My direct path gets interfered with by an obstruction. A side path gets reflected. They arrive at the receiver, but not at the same time, but you can actually physically combine them with complex weights, and then you can get some of the lost signal back again, which that maybe sounds too bizarre, but it's absolutely true. I mean, that's something Dr. Simiari is interested in too, is multiple input, multiple output channels, and 5G goes into things like that, trying to harvest the most out of a channel as possible, not just saying, I'll take the strongest signal and hopefully the weaker signals won't interfere with me, because that's the other thing that happens with multipath. Multipath is generally not considered to be good, just like if you're in a big stadium and somebody is speaking over the PA system, you get all that reverberation and all that echo that tends to make it harder to hear, right? Because you're getting the signals clobbering each other. So in radio communications, we've been dealing with this for forever, so being able to realign and combine them to all line up with signal processing can be a very good thing. Our ears don't do that though, right? At least I don't do well at that. When you have a lot of echo, you tend to, your brain gets confused. Okay, so what I wanted to now show you is a good application. This is a GitHub site that I contributed to with my co-author on a course that I taught last summer, a year ago this past summer. So it ended up in this project called GPS Helper, and I've just got it up here for the picture. There is content in here too. The idea of this was describing to the people that were taking the training how Kalman filtering works and how Kalman filtering can be used to track objects on the ground using the ranges to the satellite, from the GPS satellites to ground. So this is an exact constellation at a particular point in time, and the 4 satellites that were in view for this particular experiment had these as their codes: 32, 21, 10, and 18. And this was at a particular time of day in January of 2018, when I happened to be working at home. I pulled out my GPS receiver for backpacking and looked to see what the 4 strongest satellites were in view of my house. And I said, okay, those were the satellites, those were their PRN numbers. Then I went to my modeling tool and got the ephemeris information for those 4 satellites, which came from a database called SpaceTrack. So I got all the information on all the currently flying GPS satellites, the latest 2-line element sets, so I could propagate them using a Python package called SGP4. This is another thing great about the Python community. All I had to do was put that package on, and I've used it in past work. So I actually propagated the satellites over a period of time, and that's what these tracks are up here. These are the tracks of those satellites as they're moving, because they're in medium Earth orbit. They're not geostationary, so they are moving. And I actually then set up all the modeling with the GPS satellites and just recorded the pseudo ranges based on the distance, the geometrical distance between these satellites and this point on the ground. And then those went into a Kalman filter to actually solve for the position based on a coarse estimate, and then the filter tracks it. If you're really interested in that, it's in the repository, so it's down inside of here. And there are documentation files inside of here. And I made sure we had in here not only code, but there's also, like I said, there's Jupyter notebooks in here, and then I believe there's some PDFs of running this stuff for this particular problem. But this doesn't really use autocorrelation. This is using what you get after the autocorrelation. To actually see the autocorrelation ideas, you'd have to go over to what I did last semester in Modern DSP, and that would be Project 2. Which was this topic, GPS acquisition and tracking. So this was in on the course level of how everything works. And so a code is sent out from the transmitter. That code is received by some time delay, delta tau or delta t. And what you do in the actual processing, you form this cross correlation, because that is robust in noise, and then you note the location of that peak. And then you've got to deal with the fact that it's delayed in time, and there's also some uncertainty in there because of clock errors and things. And so the estimation problem for position is based on fusing together, say, 2, 3, 4 or more measurements of pseudo range. And that's what the GPS helper site does, but this was just building the receiver. So the receiver comes along, and this was all the waveform modeling stuff, but it's tracking this PN code, and it's doing the correlation. The local code is getting multiplied times the received code here, and then it gets filtered to form an instantaneous estimate of the autocorrelation, or actually cross-correlation. And then it tracks it with a phase lock loop kind of arrangement known as a delay lock loop. And it's definitely, in my opinion, it's cool, because it's the way it really works. So You get 3 correlators running, one on the prompt, which is the one that has the peak that you're interested in, but then in order to keep it in lock, you have an early and a late correlator that runs into a tracking loop, and ultimately it tracks the signal here with this red line, which is the peak, but it uses the early and the late to form an error signal. Nobody in here has had control systems except for Chris, right?
I've had control systems.
Didn't you take it last fall?
You talk about feedback?
Yeah.
Yeah.
He took feedback, so the early and the late correlator outputs, notice that triangle is our correlation peak. It's just how the signal processing is work. It doesn't reconstruct that entire function, it just gets samples of that function. But does this help you appreciate a little bit about autocorrelation and how valuable it can be? It's just another tool in the box of tools that are out there.
So you just show it to us, but we can't quite utilize it.
Yeah, well, if you take modern DSP, or if you want to go download this project and play with it, the code is all there. The sample code is there. They just had to do experiments with the code, so you can play with the code.
Stuff, man. It was hell.
It wasn't that bad. It works out of the box, though. You had to take some measurements and then talk about it. The Kalman filtering stuff is a little bit more exciting because in the example that I put in those notebooks, I actually put myself walking around the block in the neighborhood of where Cosmic AES is, because I had their ephemeris or lat long position, and then I set the whole thing into motion in a simulation, and then I show how well the GPS tracks, or the Kalman filter tracks position. And if I run the course faster, then it starts losing a little bit on the sharp turns where I was running like this. I'm not physically running, I'm just hypothetically running in a rectangular pattern. So I run like this and make a really sharp turn, so the GPS kind of loses it a little bit on that sharp corner because Kalman filter says, oh, he's going this way, and meanwhile I turn, but the filter hasn't quite caught up with the fact that no longer going in that direction, so it kind of overshoots and then it kind of comes back in.
Oh, it's like a dampened.
Yeah, it's an slightly underdamped kind of response. But we all do that, right? We watch it on our phone, or I can watch it on my Apple Watch if I want to, but that's something that we do. Yeah. It was up, in that case, it was updating once a second, I think is the way I had it set up. But everybody's been doing that for a long time now, and you're all just not as marveling about it because you don't understand all the details. It's all out of these sorts of ideas that it's been built, and only people like us will appreciate what it takes to make it work. The average user is like, just take it for granted. Just like turning on the microwave oven is just taken for granted, but you know there's more to it than just that.
I mean, from a surveying standpoint, though, I mean, it's a bit of a different ability to track than what you have on your watch or on your phone.
Yeah, when the accuracy.
Yeah.
Yeah.
But that's also like how you get a really accurate location is you actually have to sit there and cook and read measurements continuously from a single position.
Yeah. Well, GPS was never designed for what we're using it. It was designed for military applications, and there's a higher resolution code that they have. But then, does anybody know what president changed things for us? What U.S. president?
It was Reagan.
No, he might have had something to do with the GPS satellites, but there's something called selective availability put on the course acquisition code, which is the one we use, the short code, the course code. Then there's the fine code, which only the military can use, but still the course code had something called selective availability, which dithered the signal to make it not give very accurate course positions.
But then if you give that to people, it's kind of useless for navigation.
Yeah, so what president changed that?
Or
though?
ended in Bush because that was the...
No, it wasn't.
Really? Not the Gulf War?
Nope. Wasn't Trump. It was longer ago than that. Clinton did it. He was the one that changed it. He turned it off, but it can be turned back on at any time. And since the United States runs the thing, we can turn it back on at any time, and it's going to not make a lot of people happy, but it could be turned back on again at any time.
Suddenly it's telling you to make a very hard left off the highway.
So It's since then changed a lot of what we do in the world, though, to have that. Okay, back to some math now, finally. So a little bit more beyond what we did earlier. Earlier, I mean, we know the power spectral, we know the Fourier series representation of a periodic signal looks like this. There's actually a linkage between the Fourier series and the power spectrum and the autocorrelation function. And we got a little, kind of a little taste of that early on, but that was kind of limiting. So when we first saw this relationship, it was way back over here. It was when we noticed for a periodic signal, we can represent it like this, and then I circled that and said that Fs times Pnfs must be the Fourier coefficient. So that is just in terms of the Fourier transform of a signal, but what about the power spectrum? So that relationship, and this math is not in the book, it's just something I added and kind of couples in a little bit with Lab 2, is to say, okay, now let's try to look at what is the autocorrelation function associated with the Fourier series representation. So I just plug in the big parentheses there the two representations in there. This is like x of t, and this is x of t plus tau. So I'm actually going to try to find that autocorrelation function, which is a doubly infinite sum, but the time average operator is going to operate on the product of those complex exponentials, and because of the periodicities involved, the F naught factor involved there, the m does not equal m terms will always involve different frequencies, n times F naught, m times F naught. So if you're at different frequencies and you multiply the complex sinusoids together, you're going to get a sum or a difference, depending upon the sign. So you're always going to be at a non-zero frequency, and the time average of that is always 0, right? Because a sine and cosine wave always average to 0. So the double sum comes back down to a single sum, and finally then it comes down to then that the autocorrelation function of a periodic signal is just the magnitude of the Fourier coefficients squared times the e to the j 2 pi n f naught tau. So, and of course xn earlier was fs times p of n fs. So now there's this inherent relationship to get us to all the way to the power spectral density directly from the Fourier coefficients. It doesn't really help with more complex waveforms than like sinusoids, because you still have the issue of how do you get the Fourier coefficients for something like the PN code. So the PN code is best to just go back up to what we were talking about last time, and that is just take this on faith that somebody did the calculation and the math analysis right for an M sequence, and that is its autocorrelation function, and just Fourier transform that to get its power spectrum. But this at least allows us to get the Fourier line components of the PN code. And since in Lab 2 that's one of the things you do, how else are you going to get them? If you didn't have this, you would be like, I don't know what it's supposed to look like. So the homework problem that I already put up the solutions for, and the discussion in the lab lets you see exactly what it should look like. And I did some modeling in here, and this was how that turns out when you do it in Python. And I'm just doing the same old thing where I'm putting the values into the line spectra plotting function, but I'm putting them in as the magnitude of these x values, and the x values are now, this was done before I had things up on the GitHub, so it would be now SS, not SSD, but it's calibrated against the power spectrum idea, just using the line spectra as a plotting tool. But if that's too bothersome, you can use the stem function in Matplotlib. So before I jump into linear systems, and I'm going to run out of time, do you want to ask me your lab question, or do you want to let me do that up in my office?
We can do it now, because it'll help. Are you guys good with power spectrum density, or?
He had a question based on the lab, and
Yeah,
others of
basically
you are
it's
in the
just
lab.
deriving the power spectrum density of an arbitrary.
So it starts over here in the lab though, right?
It sounds interesting, so.
Because that would actually
You got me hooked
into
now.
how do you do power spectrum density stuff? Because I'm still fuzzy on how you get to that from some arbitrary time function.
So it comes out of the lab here, right?
Yeah.
So to guide me to the
That's what we just said.
guide me to the page. This is lab 2. So what page do you want me to go to that motivates this?
If you want to search, it's problem 1.
Okay.
Down at the bottom.
Okay.
That's only a 27-page lab?
It's a lot of
That's lab two.
background.
Lab 1 was longer. So it's 34.
Yeah. I did all this work a year ago. I was writing these labs and pretty much really working hard.
Too far.
Yeah, no, dude, you're just a masochist.
Yeah, I am.
Bringing us in.
So it's not here?
No, farther up. You're in problem 2, I'm pretty sure. No, you're all the way in problem 5. Scroll till you get problem 1.
Okay. This has got some interesting nuances in it though, for sure, right? Like that. You look at that and you say,
I don't know.
why is that happening?
Isn't that
Does anybody
similar?
know why that is?
Isn't that the sync? The sync
It is the sync, but why is it not symmetrical looking? I talk about that in the lab, but we haven't talked about it in here. But what's going on is when you move it up onto a carrier, in this case, the spectrum that's lapping down towards DC, which I guess is on my side, what it does is there's that mirror image over there in the negative frequency, and that's lapping up through. So those
so it's
two are
actually
crisscrossing.
symmetrical on a double-sided spectrum.
Yeah, because you've got these two blobs and the tails on the inside cross over each other. If you move the carrier frequency out further, then that tends to disappear.
Almost. There's a lot of code. There. Now.
Okay. So you wanted to know how do I get down to here?
So that is your arbitrary. That's an arbitrary
Pulse train.
In the time domain.
And this is what we were just looking at, right? Just moments ago. So how did I get this?
Yes.
I was just looking at that too, amazingly enough. So I'm really close. This is a good time to ask that question.
Whoa, crazy.
So now I can jump right back over to where I was and you'll
I
see
wonder
it.
if it's because like everything in this class so far relates to each other.
Yeah, I promised you that though, right? I think I did. So it's right up, it's right here.
So are you telling me that's what I need to do the lab, and we're just getting to it, but it's due Wednesday?
No, you could have looked ahead, you could have read, but yeah, I guess that's true. I don't know what Daniel's got you doing, because he hasn't asked me any questions, and
Just the standard.
okay. Well, this is it though. I mean, that part of the lab actually kind of talked about
And
that,
S
but
of F equals the
that.
yeah.
It's proven right here in the notes, but you could just take it. Yeah, you could just take it on faith, even though I had the proof. I mean, once you see it on paper, then you say, I know it must be true.
So, yeah, so it asked me to derive it. So it was what I'm supposed to do. So you have an arbitrary time domain function describing a pulse train, then you convert it to frequency domain, then you just square that frequency domain transform.
You square the Fourier coefficient.
Okay.
And so you first go from Fourier transform of one period, which we've seen, to get that.
What P means one period? DFT?
Yeah, that was the notation we were using last time.
Okay.
You're going to have a quiz question on that probably next week using that theorem, because I haven't checked you on that yet. So,
Cool.
yeah, so it just gets that, and so that comes out right here. So where did I ask that question that you're pondering?
It's not going to be anything. It's going to be the actual report.
But where did I ask you to do it, though?
On the lab. Right here.
So it's down there in the problem section.
Yep. So derive theoretical PSD of pulse train.
Okay, it's right here. I pretty much gave it to you. This was written by my trusty assistant last year,
Yeah.
and he had this rubric that he had
So
created.
that would qualify as the derivation?
Yep,
Oh, okay.
it's pretty much right there.
It's $10.
That's worth $10.
Well, all right then.
But, you know, the answers can always be right in front of you, you just don't know how to focus your attention.
Trying to like derive that. Yeah.
Yeah, it's already here. I mean, we've been hovering around the pieces, but, okay. So I have 10 minutes to do something in linear systems theory now. That's it, though.
Okay.
I hope it's not too anticlimactic.
No, I hope TA will take that as an answer.
He took this class from me last year, so I think he knows what the book is all about. Pardon me? Daniel, what's his last name? Oh, yeah. That's not right. He was in real time modern DSP. Doty. Yeah, Doty is the way I pronounce it. D-O-T-Y, right? Does he pronounce it differently? He sat in the back. He was behind you, so you didn't know who he was.
The guy that always fell asleep next to Josh?
Yeah, maybe because he's in phase.
Because he didn't sleep either, so.
He's in phase lock loops, and he's generally having a hard time staying awake. The only thing that you could do, but this is just too much nitty gritty right here. This is kind of establishing the power spectrum relationship to the Fourier series, but it's easier to just go with the answer, which is right down here. That's the answer, and then you just have to plug in the Fourier coefficients for the line spectra.
I was really confused why autocorrelation was getting tossed into the mix because he's like
Daniel was.
Yeah.
He hasn't had random signals either. He's going to be seeing it in the phase lock loops class because we need it in there. But so,
Sure, if it doesn't ask me to derive that.
and the pulse train Fourier series coefficients is on your cheat sheet. It's also in that last quiz. So you're just plugging it into here.
Okay, so I just say theorem.
You can reference this page of the notes. See, follow the derivation of the relationship between Fourier coefficients and power spectrum found on page 2-70.
I'll take it. Thank you.
You're welcome. That was a lot easier than I thought it was going to be. There's harder stuff in there than that, in my opinion, because I developed some new stuff that I'd never done before that I wrote into that lab. And then I developed a lot of Python, so that's in the notebook. I kind of worked hard at that because I wanted to replace what I had been doing using Agilent's ADS or Keysight's ADS with my own portable Python. So the next section, and this is kind of the beginning of the end of what we're going to do in this chapter, is linear time invariant systems. So this is just a review, but the idea of an LTI system. So now we can get off our signal kick and get more onto a systems kick and then start working our way along to finish off this chapter. And we're going to come back into this chapter for the Hilbert transform when we need it later. But the script H is just an operator, and in our textbook's notation, that means it's a linear operator. So linearity means that superposition holds, which means you can do what's written down in here. You can superimpose things, bring out the scale factor, and everything is true to form. This is a nice idealization. Of course, it's never true in practice because you always will reach a limit where something breaks, like you drive an amplifier too hard, what happens?
It rings.
Well, not only does it ring, it starts clipping or something, right?
It rails.
Is it linear at that point? Can you superimpose two signals and get the sum of the output?
No.
No, but that's a practical limit, though.
Yeah, my classical example is the karaoke machine, which I don't participate in karaoke, but you know what, everybody in here knows what karaoke is. It's where music is playing and then somebody gets bold enough to sing, come up and stand in front of the microphone.
Drunk enough.
Well, whatever the case may be.
Liquid courage.
So they're singing, but if the singer is so powerful or they turn the mic volume up too high, then that person's going to start overloading the amplifier and it's going to sound all splatty and distorted sounding.
Sounds like someone ate their microphone in a call.
That's an example of superposition not holding because you're now making the device nonlinear. Second main property in LTI is the I, which is the invariant, time invariant, and that just says that system is fixed, meaning that the properties of the system do not change with time. We apply an input right now, we get an output. We apply an input later, we get that same output delayed by that later amount. But the idea is that the system is not changing with time. So what's an example of a time invariant system? Anything that you build with devices that are perfectly temperature stable, there's no aging in any of the components, then you can use that subsystem any time of the day, any year, any point in time, and it's always going to remain fixed and stable. But is any system like that? No. It's all relative, though. If only you need it to stay fixed for a matter of picoseconds, that's maybe good enough. But if you need it for years and decades, I mean, a classical example I think of is cable TV. You know, around the neighborhoods in Colorado Springs, have you ever noticed those green boxes sitting around near the curb? What do you think is inside of there?
If you ever hit one with a car, you know exactly what's.
I know, that's what I was going to say. If you found one that's all burst open because it was hit and never put back together, but generally there's some cable from the cable TV, but I think they frequently have block amplifiers in there that are sitting to amplify the signal and redistribute it to different parts of the neighborhood. In other words, they don't put a lot of power at the head end of the cable, they distribute it all over the community. So they re-amplify the signal to keep the levels strong enough to get to be acceptable into your home. So those, my point though is those amplifiers sit outside in the cold and in the heat, and they have to endure a lot, and they're not perfectly time invariant. As they heat up and cool down, their characteristics will change some, not drastically, because they've been designed to have an operating temperature. But same holds true of, I guess, automotive electronics. That's a fairly harsh environment. Wouldn't you say? I mean, we expect cars to work any temperature range possible.
Yeah.
Whereas if you leave your cell phone, since Chris stood up there, if you leave your cell phone sitting inside your car and it gets really hot, what frequently will it do? It'll scream.
It'll tell you it got too hot. And shut
And
down.
you can't use it right there until it comes back to an acceptable temperature.
I don't know. Yeah, they say like up in Alaska, you got to keep your vehicles running during the winter because it gets so cold at night you can't crank them in the morning.
Yeah.
That's to do with like the oil and stuff. But
Well, yeah, the diesel engine in particular, because the diesel fuel turns to
yeah,
a
you need
jelly-like.
to be expandable, be able to expand enough to compress.
At any rate, I think that drives that point home pretty good. So once we have those two properties in place, we can fire a delta function into a system that's at rest, and then we get its characteristic, which is known as the impulse response. So my example of that would be like my finger taps the bottle, and there's an acoustical sound pressure wave, which would be sort of reminiscent of the impulse response acoustically for this transducer. You know, I'm taking my finger, hitting it, and it's emitting a sound. But electrically, if it's just an electrical impulse, it sends, the output produces that impulse response, which I look at as being a signature of the system. We could use a step, we could use anything else, but the impulse is very convenient because in modeling purposes, you can start with this idea that the book uses: let's represent a signal approximately as a finite number of delta functions with amplitude values to kind of look like this picture right here. We're going to use delta functions to approximate the waveform at a finite number of places, and then just suppose that it's a rectangular, it's held as a rectangle over that interval, and then we'll integrate x of lambda times this delta function we'll integrate x of lambda replaced by its delta function approximation, this series up over here. And that's this book's view of how the superposition, so-called superposition integral works, how you represent a convolution of an input to get an output. So this is just to approximate the signal with an integral, and series representation down below here. And then you plug all of that together inside this sum, and then you finally, I don't have the picture of that here, you finally form an approximation of the convolution integral, and then take the limit as n goes to infinity, and then finally it becomes these two results. If you don't like that for review, I guess go look in your 2610 book or circuits book or something. This is just kind of a quick way of getting at it. When you do this in the discrete time domain, which is what you first got exposed to, it's exact. There's no approximation, but it was probably not until 3205 that you saw it exact for continuous. I'm not sure what goes on in that class. You do the convolution integral, exact development,
Which class we're talking about again?
3205.
Which one is
I
that?
don't think we got that.
System.
Is that circus too?
Yeah.
No, we didn't do any convolution in circus too.
Not from what I remember.
Okay. So I know in 2610 it's hard to get that far in the continuous time domain, but
Yeah, I think we got up to discrete time and then we just stopped.
yeah, and that's the way it was when I used to teach it. So this is different from that because now we have a delta t in here because we're approximating an integral. And this is just to give you an idea how a rectangular model can be used. At this point, though, we're just running with, this idea there that x convolved with h or h convolved with x gives the output y. And then we go on to talk about some other properties, stability, transfer function by using the convolution theorem, and relationship between impulse response and frequency response, causality. So the next assignment is going to have some of these types of things on it: filters, impulse responses. There's some new things that will get introduced down the road here. A little bit of circuit theory review, but we'll introduce group delay. So that comes up.
Okay, we're gonna do RLC circuits again.
Now I'm just using it as a remember this. It's just it's a familiarity thing, but group and phase delay will get talked about.
So we haven't gotten to group delay yet, have we?
No,
That's it right there.
that was in your first lab, I know. So you were supposed to just look ahead at what this definition is what I wanted the lab instructor to tell you. Because I can't go that fast, and I never know how fast I'm going to go. And now I'm going, we're past time. As I get older and older, I go slower and slower because I tell way too many stories.
It's only because you have more stories to tell.
Exactly. But how do you resist? Sometimes you can't resist. And I have a hard time. Well, have a good weekend.